Okay, so today I'd like to talk to you about conductors, insulators, semiconductors, and band gaps. So first, let's discuss the values of some electrical resistivities for conductors, metals, semiconductors, and insulators. If you look at the values of the resistivity shown here in this chart for typical metals, you get very, very low values of the resistivity, like on the order of 10 to the minus 8, 10 to the minus 7 ohm meters. If you look at the values for semiconductors, such as carbon, germanium, or silicon, you see values ranging from, say, 10 to the minus 5, 10 to the minus 4, to a few hundred ohm meters. And then if you look at the values for insulators for the resistivity, you get very, very large values of resistivity, 10 to the 11th, all the way to 10 to the 17th ohm meters. So you can understand then that there have to be different mechanisms at play, different kinds of physics, in other words, in order to explain these vastly different values of resistivity for these materials. Now, the free electron model of conduction, which we've talked about before, it doesn't apply to semiconductors and insulators. It only applies to metals. Remember that in the free electron model, what happens is that each parent atom donates an electron or two to the sea of electrons, and then those electrons are free to move around as the charge carriers freely within the solid metal. However, insulators and semiconductors don't do this. They don't donate electrons to the sea very easily. So there's a different kind of conduction mechanism for semiconductors in particular than for normal conductors, and we need a new theory known as band theory to help explain it and conceptualize it. And the essential feature or idea behind band theory is that the allowed energy states for the electrons are nearly continuous over certain ranges called the energy bands. But then in between those allowed energy bands, there are forbidden energy gaps between them where conduction doesn't take place. So in order to understand what's going on with that, let's first look at the simplest possible thing that we can do and just talk about what happens when two atoms form a bond. So if you can imagine taking two atoms from infinity away and moving them together, you would understand that, say, they have this sort of fuzzy ball model and that the electron cloud around the atom is relatively uniform when they're very far apart. But as you push them together, the electron clouds between these two atoms begin to overlap, and then you have a region in between the two atoms where you have sort of a dense electron cloud maybe, and then a lighter electron cloud all around it. So these atoms are then bonded together because they're sort of sharing the orbitals between of the electrons in between the two atoms, all right? Now, if you wanted to figure out what the wave function for that might look like, say for one electron, then you can imagine that as you bring the electrons together, that the wave function for the two would sort of overlap and combine. Okay, so you have overlapping wave functions. And you might imagine that these wave functions can combine in various ways. You might have one that looks like this and one that looks like this, and that would give you two possible states. Well, those states would be split into two different energy levels, and there would be two ways of combining the wave functions. Now, the energy difference between those two possible states might be pretty small, so they would be close together on the energy scale. But then as you pull them apart for large values of R, they don't overlap, and then there's no splitting of the energy level. Now, you can imagine that if you take this to more than just two atoms and you have a whole bunch of atoms, as the number of atoms increases, then the number of possible combinations in which the wave functions can combine can increase, and each combination will correspond to a different energy level. And then as you add more and more atoms to a very large number of atoms, like you might see in a solid, the energy levels look like they vary continuously. Even though they are discretized, the energy levels are so close together that it looks like a continuous band. And this is where the idea of a band of energy levels comes from, that you have these wave functions that overlap, the energy differences between the various levels are so small that it looks like a continuous band of energy. So in general, a crystalline solid is going to have a large number of allowed energy bands. So here, those energy bands for the filled states are shown here in blue. So you have a 1s, a 2s, a 2p, a 3s, and so on and so forth, okay? So those bands exhibit these. Now, in between the allowed energy bands, there's these gaps, which are shown here in white. And those correspond to energies that the electrons can't occupy, or forbidden energies. And then gold here represents empty bands. For example, if this was sodium, then you would see that the 3p state is not occupied. So good electrical conductors contain a high density of free charge carriers, and here they would be the electrons, and the density of the free charge carriers in an insulator would be nearly zero. And in a semiconducting material, those are materials with charge densities in between that of insulators and conductors, and then you can use that to talk about it based upon the energy bands. So you see here three possibilities. On the left, we have a metal where you have basically unoccupied state, and they would be relatively continuous overlap in that unoccupied state band with the bands that are occupied. And so it doesn't take much for those electrons to get excited up, just a small voltage will do, and then they're free to move around throughout the metal. In a semiconductor, though, you have a forbidden gap between your occupied states and your unoccupied conduction band states, and they would have to jump up from the occupied to the unoccupied states to move around. But they don't have to jump up very far. Maybe just a few electron volts of energy is enough to get them to conduct. However, in an insulator, your valence band and your conduction band are separated by a pretty large band gap, say maybe 10 electron volts or so, and it takes a substantial amount of energy to excite that electron from the occupied valence band into the conduction band where it's free to move around. So that's the idea about the differences between conductors, insulators, and semiconductors. So in metals, to be a good conductor, the charge carriers have to be free to move in response to the electric field. And the motion of the electrons in response to the electric field is increasing the energy of the system. And when the electric field is applied to a conductor, the electrons just move up to that next higher available energy state to move around. Basically, though, you could think of these electrons as free to just move wherever they want within the conductor, hence the free electron gas model of metals. Now, at temperatures close to absolute zero, remember we have earlier talked about the Fermi energy, which is the highest occupied energy level at absolute zero. Well, you can think of the Fermi energy level as lying in the middle of a whole bunch of allowed states that the electrons are allowed to occupy. And all levels below the Fermi energy are filled, and all those above are empty. And then if you just use a small voltage and apply that to the metal, electrons having energies near the Fermi energy only require a tiny amount of initial energy from that applied field to reach those nearby empty states above it and conduct. Okay, so that's what's going on with metals and conductors. So electrons in a metal need only a weak applied electric field so that they're free to move because there's so many empty levels that are available close to the occupied energy level, so electrons are excellent conductors. However, in insulators, there's no available states that lie close in energy into which these electrons can move upward in response to an electric field so that they can move around. So although insulators do have many vacant states in the conduction band, these states are separated from the filled band by a very large energy gap, say 10 electron volts or more, and only a few electron states can occupy the higher states, so the overall electrical conductivity is very small. However, as in the case of lightning, if you do have a high enough field applied between, you can get those electrons to jump up to the next available state and conduct. It just takes a lot of energy, as you can see here from this National Geographic image. So here is a schematic of that where your conduction band and your valence band are separated by a very large energy gap. And the Fermi energy would actually lie somewhere within the gap. And at room temperature, very few electrons would be thermally excited into the conduction band. The gaps there are on the order of 10 eV, like I said. Now, the band structure of a semiconductor is similar to that of an insulator, except the energy gap is much smaller than that of an insulator. So for example, for silicon at 300 Kelvin, the energy gap is only 1.14 electron volts. And for germanium, it's even less than that, 0.67. So a reasonable amount of energy can be used to excite these electrons from the valence to the conduction band. So you can use thermal excitation. Appreciable numbers of the electrons can be thermally excited into the conduction band, or you can use a small potential difference and easily raise the energy of the electrons into that conduction band. So that's why you see very different behaviors for conductors versus semiconductors with their resistivity values versus temperature. So here on the left, for example, is a plot of resistivity versus temperature for a conductor. And you can see that as you increase the temperature of a conductor, the resistivity actually grows. It gets larger. And that's because the electrons, which are the charge carriers, scatter off the motion of the other charge carriers and defects in the lattice. And as the temperature increases, the scattering increases because the excitation and the motion gets more and more erratic. So for a semiconductor, however, you can see that the resistivity actually drops with temperature. And that's because as you increase the temperature, you have more thermal energy to excite those valence electrons into the conduction band. So you have more charge carriers as the temperature goes up, which causes the resistivity to drop. Now, charges in a semiconductor can be positive or negative or both, okay? And the reason for that is when you take an electron and you move it into the conduction band, you're actually leaving behind a vacant site. That vacant site has a positive charge, and they call it a hole. So when an electron is excited into the conduction band, you're creating what's called an electron-hole pair, and then both the electron and the hole can move through the material in response to the field. So the holes act as charge carriers, and electrons can transfer into a hole, which leaves another hole at the original site. The net effect can be viewed as the holes migrating through the material in the direction opposite the direction of the electrons. So they behave as though they were particles with a charge of plus E, or plus 1.602 times 10 to the minus 19 coulombs. There are intrinsic semiconductors. Silicon and germanium are examples of that. These are pure materials that contain only one element, and they have equal numbers of conduction electrons and holes. For every electron that moves up, it creates a hole, and those electron-hole pairs are the charge carriers. You can also tune your semiconductor if you want, or dope it. And these are extrinsic semiconductors. What you're doing there is you're adding impurity atoms to a semiconductor. So this is doping. And it modifies the band structure of the semiconductor. It can change the band gap. It modifies the resistivity and conductance. And it can be used to control the conductivity of the semiconductor. Now there's two kinds of extrinsic or doped semiconductors, and that's N-type and P-type semiconductors. In N-type semiconductors, what you do is you add an impurity which adds an electron to the structure. N stands for negative. So the impurity would be referred to as a donor atom. And semiconductors doped with donor atoms are N-type semiconductors, N meaning negative, as it's been given an extra electron. Okay, so here you see a little cartoon of that where you have your gray, regular old, say, silicon semiconductor atoms, and then they're in group 4 of the periodic table, and then you add an impurity atom with 5 outer shell electrons in group 5, and that gives an extra electron to the N-type semiconductors. The energy level of that extra electron is going to be just below the conduction band, and the electron of the donor atom can move into that conduction band as a result of a very small amount of energy. So it does modify the conductivity of the material in that way. You can also have a P-type semiconductor. Here P stands for positive, as it's been doped with an extra hole or a positive charge carrier. The impurity creates an electron deficiency, and sometimes these are referred to as acceptor atoms. Okay, so here we see our gray regular old semiconductors, say silicon, and then you're doping it with something from group 3 of the periodic table, which has one less electron, creating an extra hole. The energy of the hole is just above the valence band, and an electron from the valence band can fill the hole with just a tiny little amount of energy, leaving a hole behind in the vacant valence band, and that hole carries current in the presence of an electric field. So yet again, you can tune the conductivity of your material and change the band gap by doping. Now, in extrinsic semiconductors, you usually dope with densities that range from 10 to the 13th to 10 to the 19th doped atoms per cubic centimeter. So what you usually do is you take a group 4 semiconductor like silicon, germanium, something like that, and you dope it with a group 5 atom like arsenic or phosphorus, or a group 3 atom if you want acceptors like gallium or indium. And here you can see a schematic of that with the silicon yet again in gray, and then you have your N-type doping with phosphorus, say here in red, adding another electron. Or if you want to do P-type doping, then you would dope it with something like boron, which would leave an extra hole. Now, you can make a lot of great stuff out of semiconductors that are P-type and N-type. So one way to do that is just take a P-type semiconductor and place it right next to an N-type semiconductor and create what's called a p-n junction. A basic p-n junction creates a diode that allows electricity to flow in one direction but not the other. Here from this diagram we can see a diode where the N-type material has free electrons shown as black dots and the P-type material has holes shown as white dots. Now near the p-n junction what happens is the electrons diffuse into those vacant holes in the P material, and this creates what's called a depletion zone. The depletion zone acts like an insulator which prevents other free electrons in the N-type silicon and holes in the P-type silicon from combining. In addition, this leaves a small electrical imbalance inside the crystal. Since the N region is missing some electrons, it's obtained a positive charge, and the extra electrons that filled the holes in the P region have given it a negative charge. Now, if it's just sitting there, this doesn't create any electricity. However, if you apply a voltage to it, an external power source, then you've got a junction diode with a forward bias. So here we've connected an external power source, a battery with a light and a current meter that indicate current flow. The negative terminal of the battery is connected to the N-type silicon, and the like charges repel, so the free electrons are pushed toward the p-n junction. Similarly, the hole are repelled by the positive terminal of the battery towards the p-n junction. If the voltage pushing the electrons in the holes has sufficient strength to overcome that depletion zone, which is typically 0.7 volts for, say, a silicon diode, then the electron and holes combine at the junction and current passes through the diode. And when the diode's arranged in this way with the power supply, it's said to be forward biased. And so you get current flow when you have your diode in a forward bias. However, if you try to apply the voltage in the opposite direction, you do not get current flow. In this diagram, the battery is connected to the diode so that the negative terminal of the battery connects to the P-type silicon and the positive terminal of the battery connects to the N-type silicon. The negative terminal attracts the positive holes in the P-type silicon and the positive terminal of the battery attracts the free electrons in the N-type silicon. All the charge carriers are pulled away from the p-n junction, which essentially creates a larger depletion region and no current flows. And when a diode's arranged this way with the power supply, it's said to be reversed biased. Now, you can use diodes for other things than just sort of a gate allowing current to flow with voltage in one way or not allowing it to flow in the other. And you're probably really familiar with LEDs or light-emitting diodes already. So whenever an electron makes a transition from the conduction band to the valence band, which effectively recombines the electron in the hole, there's a release of energy. So if your electron drops down, then that means that in order to satisfy energy conservation, energy must be emitted, usually in the form of a photon. In some materials, the energy levels are spaced so that the photon's in the visible part of the spectrum, and in this case, the continuous flow of current through the LED results in a continuous stream of nearly monochromatic light. As you can see here, these LEDs have all kinds of groovy colors depending on what your band gap energy is. So the application of a forward bias to the diode causes electrons to flow into the P region from the N region and holes to flow into the N region from the P region. And when they enter the new region, the carriers constitute minority carriers amongst majority carrier type, which rapidly leads to recombination. And in the direct recombination process, an electron from the conduction band falls into a hole in the valence band while conserving energy by emitting a photon, as shown above. Most emitted photons have an energy equivalent to the band gap energy, and the band gap of the material can therefore determine the color of the emitted light, and that can be modified by changing the semiconductor material or doping it differently. So LEDs, diodes, two of the groovy little devices that you can create from semiconducting materials. More importantly, arguably, is the transistor. So, for example, let's talk about the field effect transistor, and that's a device which enables us to use one electrical signal to control another. In fact, the name transistor is actually a shortened version of the original term, which was transfer resistor, and that indicates how the device works. Most transistors have 3 connections, and the voltage on the current into or out of one wire has the effect of controlling the ease with which current can move between the other 2 terminals. And the effect there is to make resistance whose value can be altered by the input signal. And we can use this behavior to transfer patterns of signal fluctuation from a small input signal into a larger output signal. So here is pictured an N-channel junction field effect transistor. So this sort of transistor is made by forming a channel of N-type material in a substrate of P-type material. 3 wires are connected to the device, 1 wire at each end of the channel, and 1's connected to the substrate. Electrons can move along the channel, so when we apply a voltage between the 2 end wires, a current will flow along the channel, and we can maintain this by continually putting electrons in one end, which is the emitter, and removing them at the other, which is called the collector. And the effective resistance between the 2 ends will depend upon the size and shape of the channel and the properties of the N-type material. Note, however, that the electrons moving in the channel will, just as with the diode, be repelled by the fixed charges in the P-type substrate, and as a result, the current doesn't fill the whole channel. It avoids the depletion zones near the walls. If the 3rd wire is used to apply a small negative voltage to the gate or the base, then that increases the forces which push channel electrons away from the walls. And as a result, the depletion zones get bigger and the cross-sectional area the current has to squeeze through gets smaller. If the voltage is large enough, we can reduce the flow to 0 and pinch off the current. And the 3rd connection is often called the gate for that reason, because it can be used to control the flow of electrons along the channel. And if we wish, we can apply a small positive voltage to the gate, making the depletion zone smaller and let the current flow more easily. But you can't take it too far. If you apply too large a gate voltage, will make it possible for the channel electrons to cross the walls and move into the substrate, and that won't help us get them moving from source to drain, so it isn't any use. What's worse, modern field effect transistors have such tiny gates that even a small channel gate current will blow up the transistor, so you got to be careful. Now, photovoltaic cells are another exciting application of semiconducting materials. So this is closely related to the light-emitting diode. It's kind of a light-emitting diode in reverse. What happens in a solar cell is it takes incoming light energy and turns it into electrical energy. So in this case, you have a p-n junction diode, for example, which can absorb a photon of solar radiation by having an electron make a transition from the valence band to the conduction band. And in doing so, a conducting electron and a hole are created. And if you connect a circuit to that junction, then the holes and electrons will move so as to create a current, with a positive current flowing from the p side to the n side. So that's basically what a photovoltaic cell is, a p-n junction in reverse. And then finally, our lives would be very different these days if it weren't for integrated circuits. This is arguably the most important use of all these semiconductor devices today. And it's not really that they're used in discrete components, but assembled into an integrated circuit or a chip. And then some of these integrated circuits contain 1 million or more components like resistors, capacitors, transistors, and logic switches, all miniaturized and condensed down to a very small chip. And of course, the benefit of miniaturization is that if you put your things smaller and closer together, current flows from one device to another much more rapidly, enable them to move more rapidly so their processing speed goes way up. All right, so that's all I want to tell you in this brief introduction to semiconductors and band gaps and semiconductor technologies. This lecture was not at all original. I assembled it from many sources that are cited on the slides, and I encourage you to check out those references. And if you need help in the future finding more interesting reading on this subject, come to me and I'll be happy to point you in the right direction. Thanks a lot.